Now that we're thoroughly familiar with the computational as well as the geometric aspects of partial derivatives, it's time to talk about multivariable differentiation in all its full abstract glory. And basically the idea is, of course, that you want to approximate shapes with tangent planes, and we will do so first for parametric surfaces, because that's where I think the geometry is most intuitive, even though the parametrizations, of course, are a bit more technical. Then we're going to take a look at it for multivariable functions, which can be, of course, viewed as parametric surfaces. We will look at applications of the whole thing, especially when we're doing error estimates of multivariable functions. And all of those parts of this presentation will be under the assumption that everything works well, and then we'll come to the part that in previous presentations we have called pathology, where we're going to look at examples where things don't quite work so well anymore, but this time around we will resolve the pathology with the abstract definition of multivariable differentiability, because now we're really ready to see that thing fully in 3 dimensions and also symbolically. And we will close out with a little bit on implicit differentiation. Now, it's not that typical that people start this with parametric surfaces, because parametric surfaces are a more demanding concept than functions of several variables, but at the same time, parametric surfaces are the tools that allow us to encode any surface of any object in 3-dimensional space, and therefore it is my opinion, and I might be alone in that, but I try to back it up, it is my opinion that we should face parametric surfaces as much as possible, simply because they are such a universal tool. So let's take a look at how we could define tangent planes. So basically, we have seen in the previous presentation situations in which we can compute slopes in something that should be a tangent plane, but at the same time the function can even be discontinuous nonetheless. And this is a sad state of affairs indeed. I didn't even try to fake that, but at times like these I wish I really had a good British accent that I could mimic. Well, now to resolve this sad state of affairs, it's time to determine the abstract conditions that prevent these pathologies from happening, and that will be what we talk about in multivariable differentiability. Alright, so let's take a look at parametric surfaces. The idea behind a parametric surface is that we have a parameter domain for parameters u and v, and that domain is mapped by a function which is called surface of u and v to a sheet that sits in 3-dimensional space, which is the parametric surface. And if we now hold u equals constant, well, then in the parameter domain we get vertical lines, and these vertical lines are being mapped to coordinate curves u equals constant on the parametric surface. And of course the nice thing of these parametric curves is, of these coordinate curves, is these are parametric curves, and for those things we know how to take derivatives, right? Of course we can also hold v equals constant. We get horizontal lines in the parameter domain, and then coordinate curves v equals constant on the parametric surface. These coordinate curves are parametric curves, and so if I now take a look at the rate of change of these curves in, say, the u direction, well, then I would just take the partial derivative of this curve with respect to u. The technical aspect is very simple, right? We hold v equals constant, that gives us a parametric curve, and we take the derivative of that with respect to its input parameter. And so that would give us a vector that is tangential to this parametric curve. We can also hold u equals constant and compute the rate of change in the v direction, which would be the derivative of this parametric curve here, and so that gives us a vector that is tangential to the blue curve, and we can denote that vector ds dv. But then, of course, the interesting thing is, once we've got two vectors that are tangential to the surface, and they ought to be tangential if they're tangential to the coordinate lines on that surface, then these two vectors span a plane, and that plane ought to be the coordinate plane. Of course, here again, we have to make sure that the right abstract condition is satisfied. Right now, we are looking at this visualization under the assumption that everything works out nicely. Okay, so that picture is a little bit cluttered, so let's do it again with just single coordinate curves. So again, we have a coordinate domain for u and v. We have a function, the parametric surface of u and v, that maps this domain to this two-dimensional sheet in three-dimensional space. And if we hold u equals constant, we get a single parametric curve on the surface this time around. If we hold v equals constant, we get a single parametric curve, v equals constant on the parametric surface. And now again, the rate of change in the u direction for this curve v equals constant is just the tangent vector ultimately of that curve, and that's denoted ds du. Similarly, the rate of change in the v direction of the blue curve gives us another tangent vector, and as long as the surface is well behaved, which it typically is in applications, then these two vectors, ds du and ds dv, span a plane, because the ds du vector gives us a line that is tangential to the surface. The ds dv vector gives us a line that is also tangential to the surface, and these two lines ultimately then, or these two vectors, span this plane. So we can really see here that this plane ought to smoothly fit things. How does this work as an abstract definition? Well, first of all, we technically have to define what it means to take a partial derivative of a vector-valued function of m variables. But that shouldn't be so bad, because the partial derivative, or anything that we do with a vector-valued function that has an analog for single-variable functions, typically is done component-wise. And so the derivative of this vector-valued function with respect to its ith input variable ti, which is also r sub ti of t1 through tm, is nothing but the partial derivative of the first component with respect to ti, partial derivative of the second component with respect to ti, all the way through partial derivative of the nth component with respect to ti. So this notation, even if we hadn't defined it, we ought to have been able to interpret that correctly. And of course, that only works whenever the partial derivatives of all the components exist. Otherwise, the function doesn't have that partial derivative at that particular point. Okay, so now, if the necessary derivatives of the components of the parametric surface S of u and v exist at the point u0, v0, well, then the plane that is given by plane of AB being S of u0, v0, which would be our base point, right, plus one parameter times the direction vector in the u direction, if you will, the S sub u at u0, v0, plus parameter times the direction vector in the v direction, the S sub v at u sub 0, v sub 0. Well, that's a plane, because it's base point plus parameter times one direction plus second parameter times another direction, that plane. Or the plane alternatively is also given by the vector equation of the plane, where you take your direction vectors S sub u and S sub v and take your cross product of that, and what that gives you, of course, is a vector that is perpendicular to what is supposed to be the plane, and then point in the plane minus base point is perpendicular to that normal vector, and so this dot product would be 0 for all the points in that plane. So that's just a different way of expressing the same plane. That plane is called the tangent plane of the surface S of u and v at the point S of u0, v0, and I think I've got a picture for that on the right here, and that is again that we, one more time, and you will keep seeing this visualization of parametric surfaces as something where we take a parameter domain for u and v that by a function, surface of u and v, is mapped to a sheet. You will see this animation over and over again, because I really want us to internalize what parametric surfaces do, because they simply, even though they are technical, because they simply are so useful throughout science. Okay, so then we have the surface here, and if we hold u equals constant, we get our coordinate line. If we hold v equals constant, we get another coordinate line. If we take a step in the u direction, we get a tangential vector S sub u, or ds du. If we take a step in the v direction, we get a tangential vector ds dv. And these vectors, which would be this one and that one, are the direction vectors for a tangent plane. And if we have an arbitrary point in that tangent plane, and then this point here would be our base point, well then r minus S of u0, v0 would be a direction that is inside the plane, and of course the cross product of these two vectors would be a normal vector that is perpendicular to this tangent plane. All right. Well, let's just look at a computational example. And so for the cylinder S of u and v being 3 cosine u, 3 sine u, and v, where u goes from 0 to 2 pi, goes all the way around, so it's a full cylinder, and v goes from 0 to 4, well, so that thing has bounded height, if you will, and it's of course only the walls of the cylinder. We don't have the top and bottom there. We want to compute the equation of the tangent plane at the point 3/2, 3/2 root 3, and 2. Can that point be reached? Well, if we set v equals 2, we get that the z-coordinate is 2. And if 3 cosine of u is 3/2, which would mean cosine of u is 1/2, which would mean that u is pi over 3. Well, for u equals pi over 3, we get 3 cosine u being 3/2 and 3 sine u being 3/2 root 3. So this really is a point on that surface. And we want to compute the equation of the tangent plane at that point. And, well, yeah, here's hopefully our favorite box, because it is just computation. We had the formulas on the previous panel, and so we can just take the derivative of s with respect to u, which is partial with respect to u of 3 cosine u, 3 sine u, and v, which should give us negative 3 sine u, 3 cosine u, and 0, and that's exactly what it is. And if we take that partial at the parameter values that we had already worked out, pi over 3 and 2, we end up with negative 3/2 root 2, 3/2, and 0. Negative 3/2 root 3, sorry, that was genuinely misspoken. But yeah, so negative 3/2 root 3, 3/2, and 0. We take the partial with respect to v, well, so that's partial with respect to v of 3 cosine u, 3 sine u, and v, which would give us 0, 0, and 1, because only the third component depends on v, and the third component depends on v in a very simple fashion. That gives us the partial with respect to v at pi over 3 and 2 for the parameter values is just 0, 0, 1. And so these two vectors are the direction vectors for that tangent plane. And so the parametric equations of that plane are that the plane of A and B would be our base point, 3/2, 3/2 root 3 and 2, plus parameter times first direction vector, negative 3/2 root 3, 3/2, and 0, which we have right here, plus second parameter times second direction vector, 0, 0, 1. If we now want to visualize what that looks like, well, we would just put that into a computer algebra system, and that's what I have done here in MathCAD. The blue part is the cylinder, the orange part is the plane, and we can really see that this plane acts very tangential to the cylinder. If we look at it from all these possible directions, we really see that the plane is tangential to that cylinder. It fits that cylinder in a very nice and smooth fashion. And that's what a tangent plane is supposed to do, right? Okay, so, well, we move on. And typical presentations talk about multivariable functions first and then talk about slopes in 3 dimensions, which you somehow stitch together. I really prefer to see the 3-dimensional image first, and if we have that, we can also do a symbolic translation to functions, but we will also look at the picture. And so a function, of course, we can always translate a function into a parametric surface as surface of x and y, being xy, f of xy, right? That is why, again, I keep making commercials for parametric surfaces here, but that is, again, why parametric surfaces are so useful, because functions are just special cases. If I simply take the x input and the y input as the x and y variables of a parametric surface and then put the function in the third variable, I encode exactly the same graph. Okay, so if we now consider the point ax, ay, well, then the tangent plane of that surface of u and v, actually I call those variables now u and v, would be that I take my base point ax, ay, and f of ax plus ay, plus parameter times the derivative of this with respect to the first variable, the derivative of x, is 1, the derivative of y with respect to x is 0, and the derivative of f with respect to x is, of course, just the partial of f with respect to x at that point, plus second parameter times the y derivative, well, dx dy, partial of x with respect to y is 0, the partial of y with respect to itself is 1, and the partial of f with respect to y is just the partial of f with respect to y at that point. So that would be the equation of the tangent plane for a function that we view as a parametric surface. Well, a function we don't want to necessarily always view as a parametric surface, and so we'd like to have the equation of the tangent plane as a function also. And to do that, well, we realize that if we read this component-wise, we have that x is ax plus u, we have that y is ay plus v, and we have that z is f of ax plus ay plus u times partial of f with respect to x at the point plus v times the partial of f with respect to y at the point. Well, that's almost where we want to be, but we don't want to have z in terms of u and v. We want to have z in terms of x and y, and that's, of course, easily done because u is x minus ay, and u is x minus ax, and v is equal to y minus ay, and if we plug that in, we get that z is f of ax and ay plus the partial of f with respect to x at the point where we want to take the tangent plane times x minus ax, which is the x distance from the point at which we are taking the tangent plane, plus the partial of f with respect to y at ax and ay times y minus ay, so also times the component of the displacement in the y direction. If we want to do that abstractly, we of course would be interested in functions of invariables. And so if we have a function f that is a function of invariables whose first partial derivatives exist at the point a1 through an, then we define the tangent hyperplane of f at a to be the following. And again, it's a hyperplane if we've got more than two variables, otherwise it's a tangent plane. And we define that to be z equals f of a1 through an, the value at the point where we want to find the plane, plus the sum j equals 1 to n partial derivative with respect to xj of f at the point where we take the tangent plane times xj minus aj. Now there are various symbolic analogies to the equation of the tangent line, because if n is equal to 1, this is really just the tangent line of a function z equals f of x. But what I would always want to see, you want to have a geometric understanding of what's going on, and that's certainly also then where we can look at the picture that people often draw for this thing. So if we look at a function of just two variables on an xy domain in an xyz coordinate system, we have an xy domain, we have a graph of a function of two variables. Well, then we take a point where we want to find the tangent plane, and basically we're doing the same thing as with these parametric surfaces, right? If we hold y constant and let x run, then we basically go along a straight line, which induces a coordinate line also on the graph. If we hold x constant and let y run, we get a straight line in the domain, which introduces a coordinate line on the surface. And if we then take the derivative in the x direction, we are getting a vector or a slope in the x direction. And that, of course, defines then a direction for a tangent plane. If we take the derivative in the y direction, we get a slope that also defines a vector here, which gives us a y direction. And if we put a vector that gives us the direction of the tangent plane in the y direction, if we put that together, we get the geometric quantities that define a tangent plane. And if we then want to view this thing as a function, well, we've got the base point here, that is f of x or ax, ay. And then we have that for whatever displacement we have, say, in the x direction, so x minus ax, we would go a certain number of steps down in this case, because this partial derivative with respect to x looks like it is negative, and for any step in the y direction we could go almost horizontally here, and these two directions together then piece together the equation of a tangent plane. Alright, so as an example, well, find the equation of the tangent plane of the function f of xy equals 10 minus 3x squared minus y squared at the point 1, 2, 3 if that tangent plane exists. So the it refers to the tangent plane, not to the point, which of course does exist. Quick double check, if x is equal to 1 and y is equal to 2, we have 10 minus 3 minus 4, which really is 3. So the point 1, 2, 3 really is on the surface. And I could have put my little green box here again because the rest is just computation. What do we need for the tangent plane? We need the partial derivative in the x direction, which is negative 6. And that means that the partial derivative in the x direction at 1, 2 is negative 6 by itself. The partial derivative in the y direction is negative 2y, which means that the partial derivative at the point 1, 2 in the y direction is negative 4. And that means that the tangent plane z is z value at the point 3 plus, which in this case is then plus negative 6, so minus 6 times x minus the x coordinate of the base point, which is 1, plus negative 4, so minus 4 times y minus the y coordinate of the base point, which is 2, so we get a y minus 2 there. And if we want to visualize that, I have another MathCAD sheet. The surface, of course, is a paraboloid. It's a fairly steep paraboloid, which we can see here in blue. The tangent plane is again orange. That I think is going to be a little bit of a convention here. And if we rotate that around, again, we can see that even though this is, of course, a bit more of an extreme picture, the tangent plane really fits this paraboloid rather smoothly. And even if we look at it from below, we can see, again, we've got a pretty smooth fit here. And basically, the idea behind the tangent plane in these images is that anytime we view the tangent plane edge on it, it should look sort of like a tangent line, right? Because the tangent plane is, of course, a higher dimensional analog of a tangent line. And if we were to take cross sections, then the plane would become a line, the surface would become, in the cross section, would be a curve, and the tangent plane should be then a tangent line to that cross-sectional curve. And so all of that works very well. And these computations, of course, again, I mean, look, you've got the formulas. You certainly want to remember and understand the formulas. But once you have those, the computations aren't that bad. This is all nice geometry. And that's great. But certainly scientists, once they have encoded things, and for the longest time, the encoding really wasn't the most important thing on scientists' mind. So therefore, what were scientists using these kinds of things for? Well, technically they were using it for a process called linearization of more complicated processes, which is really something that you would see more in advanced classes. But one thing that you have seen in labs potentially already is that these partial derivatives are also used to do error estimates. Because basically, if you have a function such that the gradient of the function at a exists, well, then we can define the linear approximation of the function of f at a to be linear approximation at the point a, evaluated at r, being the value of the function at a, plus the gradient at a times the displacement from a, which is a minus r minus a, and of course when I say times, I mean the dot product here. This is of course nothing but value at a plus the sum j equals 1 to n of the partial derivatives in all the directions times delta xj, where delta xj is xj minus aj, which is the jth component of the displacement r minus a of the place r where we want to evaluate the linear approximation from a. If you look at this, this is nothing else but the tangent plane. It is now just viewed a little bit differently. And what happens sometimes when models are too complicated is that if your model, you're only interested in your model in a small neighborhood of a point where these displacements r minus a are small, then basically as long as multivariable differentiability is satisfied, your function is very close to the linear approximation, and so the function can be replaced by the linear approximation then, and that makes certain computations simpler. We can look at that for error estimates, and so if we've got a function that is differentiable at x1 through xn, all right, that's something that I'll still have to define, but it's just going to be partials and another technical condition are satisfied. So then we let delta xj to be error estimates for the input values x1 through xn. Well, then the error of the output value is reported as that the actual error is still distorted value minus actual value. That would be the actual value of the error. That's capital delta of y. Well, we are going to report that as approximately being lowercase value delta y, which lowercase delta y, which is sum j equals 1 to n absolute value of the partial derivative with respect to xj at the measured value times the error estimate in the xj direction. And so this is basically nothing else but the linear approximation with the actual value subtracted off. You can compare that with what we had on the previous panel. And that makes sense because basically the delta xj is an estimate as to how far away you could be with your inputs from the input point x1 through xn. And we have just seen in the linear approximation that the partial derivatives just act as magnification factors for these potential disruptions. And we have to take these things as absolute values because we don't know whether or not the errors in the various directions cancel out or not. Of course, we hope that we will, but we cannot assume that they do. So as an example, if you're looking at the oscillation period of a spring mass system, well, we know that that is given by t being 2 pi times square root of the mass of the spring mass system divided by the spring constant of the spring. I want us to find the error that we get for the measured oscillation period if we have measured that our spring constant is 10.0 newtons per meter plus minus 0.03 newtons per meter, and if we have measured the mass as 0.5 kilograms plus minus 0.002 kilograms. So a spring mass system, of course, is something that you may well have already seen in physics classes. It's a spring to which a mass is attached, and if I remember taking that picture correct, that might actually be a half kilogram mass. That is it? No, that's I think that's only 200 grams. Okay, well, either way, it's just a visualization. So if you attach a mass, well, that mass can be weighed, but your scale will have finite accuracy, and so I'm assuming here that that scale goes down to grams and maybe not quite so well anymore. You hopefully will have better scales. And similarly, when you measure the spring constant, you have various measurements that have errors attached to them, which ultimately make the spring constant measurement not that accurate necessarily. And well, then what we want to do is we want to compute the error. And what do? Again, the rest is computation. We have the error formula. We want to have the partial of t with respect to m, which is 2 pi times the derivative of the square root, which is 1 over 2 times square root of what's inside, which is m over k, times the derivative of the inside with respect to m, which is 1 over k. Well, the 2's cancel, and we end up with pi over root m times k, because k divided by root k in the denominator just gives us a root k in the denominator. Partial of t with respect to k, similar story. The derivative, we keep the 2 pi. The derivative of the square root function is 1 over 2 times root 2 times root of whatever is inside, which is m over k. Then by chain rule, we have to take the derivative with respect to k of the inside. Well, that is m times k to the negative 1. The derivative would be negative m times k to the negative 2, which is negative m over k squared. And if we simplify that, well, again, the 2's cancel. This time m over root m gives us a root m in the numerator. And square root k squared is the square root of k to the fourth divided by square root of k in the denominator, gives us a k cubed in the denominator. Then if we look at delta t, well, delta t is therefore approximately partial with respect to m times delta m plus partial with respect to k times delta k, which gives us pi over square root of 0.5 kilogram times 10 kilograms per second squared times the delta m, which is 0.002 kilogram, plus the partial with respect to k, which is pi times, and we use an absolute value, so this minus sign doesn't do anything. So plus the absolute value of the partial with respect to k, which is pi times the square root of the mass, which is 0.5 kilogram, divided by k cubed, which is now 1,000 cubic kilograms, divided by seconds to the sixth. That's, don't try to visualize what that may be, times 0.03 kilogram per second squared. Well, let's see, what is that? Newton is kilogram times meters per second squared, divided by meters gives us kilograms per second squared. The quick sanity check we can do is a unit check. The first one has in the denominator kilogram squared and then the square root of that. That cancels with the kilograms, leaving us with in the denominator a square root of 1 over second squared, which is 1 over seconds, and then 1 over seconds is just seconds. So that first one here has a time unit. If I'm looking at this one, the kilogram with a kilogram cubed gives us 1 over kilogram squared under the square root, which gives us 1 over kilogram, which cancels with this kilogram here. And we also get 1 over second cubed under the square root, 1 over second to the sixth underneath the square root. I already took the root there. And so if you take 1 over second to the sixth, that is second to the sixth under the square root gives us second cubed, and second cubed divided by second squared is seconds. So this one also has a time unit as it should be. And that gives us then, when you work it out with a calculator, that the error is approximately 0.0049 seconds. So that tells us that even if we have a comparatively crude measurement of the spring constant as well as of the mass, we're getting a pretty good measurement of the period of the pendulum out of it, because this is accurate down to 5/100ths of a second. And then, of course, with the convention that we have for error reporting, we only report the first place of the error, unless the first place of the error is a 1, in which case we report the first 2 places of the error. All right. So this is how you do error estimates. If you've done that in labs before, then this is familiar to you. If not, next time you do it next time you have to do error estimates in a lab, you may have to go through this process. All right, so now let's come to multivariable differentiability. This is something that I have deliberately delayed because even though it is mathematically very important in most applications, it just works out because we have very strong hypotheses in many realistic models. So in order to motivate multivariable differentiability, let's think about single variable differentiability again. The single variable derivative tells us that f prime at a is the limit as x goes to a of f of x minus f of a divided by x minus a. And for a multivariable function, I can't do that technically because I cannot divide by the difference of two vectors, because I cannot divide by a vector. So, of course, I could just try to do some algebra with this, and I can bring the f prime of a over here, and if this limit of the difference quotient minus this number is equal to 0, that is the same as what I get when I take the limit and I put the f prime of a on the fraction, right? I still have f of x minus f of a divided by x minus a, and I just have here f prime of a, which when the x minus a is cancelled is just the f prime of a. But now I have output divided by input, and the right hand side, the limit is 0, so I could now just, I can take out the negative sign, and I get f of x minus f of a plus f prime of a times x minus a, that limit is equal to 0. And now here we recognize something, because this is the equation of the tangent line. And so basically what that means is that single variable differentiability actually just says that the limit of f of x of f minus its linear approximation must be 0, and the difference must go to 0 faster than x minus a. And now this is something that we can translate to multivariable functions, because for multivariable functions we have the function, we have the linear approximation, and the x minus a is something that we could replace with a norm. And so the definition of multivariable differentiability is that the multivariable function f is differentiable at the point a if and only if the linear approximation La exists, and the limit as our point r goes to a of value of the function at r minus linear approximation at r absolute value divided by the distance from this point from a is equal to 0. So basically what that means is not only must those partial derivatives exist so that I can define the linear approximation or the tangent plane, but the difference between the function and its tangent plane must go to 0 very, very fast. It must go to 0 faster than the distance of the point at which we compute this difference from a. And so this really is what we have also seen with this tangent plane here. Basically, if we look at this tangent plane, then, well, let's look at it in a way where it fits the surface a little bit nicer. So if we look at this tangent plane here, of course, at this point, the difference between the tangent plane and the function goes to 0, but basically it has to go to 0 faster than something else that goes to 0, which ultimately then forces this very smooth fit here. And that's, of course, what we want to have for a tangent plane. A tangent plane is supposed to fit the shape that it approximates very smoothly. Okay, so this is equivalent to saying that f of r minus linear approximation at the point a evaluated at r is equal to epsilon times r minus a, where epsilon goes to 0 as r approaches a, and that is really often the abstract definition of multivariable differentiability that is being quoted, and that is because this is the handiest way to define multivariable differentiability and use it in further abstract classes, which really would pretty much pick up right here where we're going to stop, where this is more of a capstone for our multivariable calculus class. And so now let's look at that again. Basically, if the difference is epsilon times r minus a, well, okay, so r minus a goes to 0 sort of like a straight line, and if we multiply that with something that also goes to 0 as r approaches a, then basically we get something that goes to 0 on the order, that's not quite technically correct, but it goes to 0 on the order of difference to the 1 plus epsilon. And so if you look at difference to the 1 plus epsilon, such as, say, difference to the difference squared, then you get something like a quadratic fit, which is sort of like what happens here. And that's what we then ultimately, of course, understand as being smooth. The function, respectively, the surface are a smooth curve, respectively surface, and that curve and surface are smoothly fitted by the tangent line or tangent plane. Okay, so then as a theorem, if a function of n variables is differentiable at a point a, then it is continuous at a. That is, of course, what we'd like to have, because that is what we have for single variable differentiability. This proof is now definitely at the high end of what we're doing, but it's not that bad, because if the function is differentiable at a, we know that the limit as r goes to a of f of r minus linear approximation taken at a evaluated at r, that limit of this of the absolute value of this difference is 0. Therefore, because we also know that the limit as r goes to a of gradient of f at a dot r minus a, well, r minus a goes to 0, so this goes to 0. That means that the limit as r goes to a of f of r minus f of a is the limit as r goes to a f of r minus f of a plus gradient times r minus a, because I've just added 0 because I've added something whose limit is 0, and that is 0 because this is the limit of f of r minus L sub a of r. And so that means that the limit as r goes to a of f of r is f of a because the limit of the difference is 0, and that means that f is continuous at a. So that now removes the pathologies that we have seen in the earlier presentations. If a function f of n variables is differentiable at a, then it will also be continuous. Of course, it means we have to contend with the technical definition of multivariable differentiability. As an example, let's take a look at this butterfly shape function that we had also analyzed that was had partial derivatives in all directions, but which we didn't think could fit a tangent plane that well. And so that was that f of xy is x squared y over x squared plus y squared for xy not being 0 and 0 for xy being 0. We want to show that that is not differentiable at the origin. Well, let us just go ahead and take the difference of the function with the linear approximation, divide that by the difference between the point at which we evaluate the difference and the base point, which is of course 0, the origin, 0, 0. Well, that gives us that the linear approximation, of course, is 0 because we know that the gradient of this thing at the origin is 0. That was something we computed in the previous presentation. And we also know that the value of the function is 0, so the linear approximation ends up being 0. F of r cosine theta r sine theta, we've already worked that out before in the previous presentation. We have a y and an x squared, so we get an r cubed, and then we get a cosine squared theta from the x squared and a sine theta from the y. And of course, the denominator is x squared plus y squared, which is r squared, because this is nothing but polar coordinates, so we get an r squared here, and then we divide by the distance of the point r cosine theta r sine theta from the origin, which is just r, and that is just, as we simplify, that's r cosine squared theta sine theta, because we canceled the r squared, and we can cancel another r, that is cosine squared theta sine theta. And remember, for this function to be differentiable at the origin, we would have to have that this thing goes to 0 as r goes to 0, and we realize here that this is root 2 over 4 when theta is pi over 4, because when theta is pi over 4, what do we get? We get 1/2 root 2 for the cosine, we get 1/2 root 2 for the sine, which gives us 1/8 root 2 cubed, and that's 2 root 2 divided by 8, and that is root 2 over 4. So that works out, and that of course is not equal to 0, so the function is not differentiable. And if we want to look at that graphically, well, if our let's see, if our x-axis goes this way and our y-axis goes that way, then theta equals pi over 4 is right here, and we can see that yes, this thing goes out with a positive slope, which is not 0, which is not the 0 slope that we would want to have along the axes, and that is why this function is not differentiable at the origin. We can try to fit a tangent plane, but there will always be parts of the tangent plane that just don't fit the other directions that this function has, even though the function is nice and continuous at the origin. Okay, so a couple of theorems that we're briefly just going to review, and we're going to revisit the multivariable chain rule. We're not going to reprove it here, but basically if we have a function of n variables that is differentiable at the point a1 through an, and if the inputs are, and if we have inputs xi depending on variables u1 through um, so that xi of u1 through um is ai for all I, and the components xi are differentiable with respect to ti at u1 through um. Okay, so we're looking at the notion of differentiability here, certainly for the f as well as for the inputs. If all of that is the case, then with r being the input vector x1 through xn, which we shall interpret as an input vector in space, we have that f of r of t1 through tm, or u1 through um, is of t1 through tm is differentiable with respect to ti at the point u1 through um, because we wanted to have that the point u1 through um for the input gives us the ai's that we want to plug into f. And we have that the partial of f with respect to ti is the gradient of f at r of u1 through um dot partial with respect to ti of r of u1 through um. Now this theorem is mathematically nice because we have weaker hypothesis than what we had before when we talked about the chain rule, where we assumed continuous partial derivatives. And this is something that mathematicians are interested in because mathematical theorems are supposed to work in the most general settings, and that means we like to have weakest possible hypotheses, and that is why very often multivariable differentiability is presented before people talk about the chain rule, because that way the theorem can be stated in all its full strength. At the same time, what we get out of it is that we can take partial derivatives, that we can take the overall derivative then also, which is the tangent plane, and we can take it in the form that we have also already seen, which is that we take the gradient of the outer function and take the dot product with the partial derivative of the inner function, which means that the formula is very simple, similar to the single variable result. However, we can also see an obvious drawback to this theorem, especially for people who are not accustomed and haven't been working at this abstract level for a while, and I would, no offense intended, I would count you guys among that group, and that is that this theorem is really, really technical. I mean, we have to talk about the function just being differentiable at the point. We have to talk about the input function separately being differentiable with respect to ti at the input point for the xi that gives us the input point a at which the function f is defined. And that means there's an awful lot of detail to keep track of, which, and here's where I hope that my mathematical colleagues will not consider me a heretic, but most of the time these hypotheses are satisfied in applications. In fact, they're satisfied with much more strength than just this. And so typically, and we're going to talk about that too, typically, unless you're looking at really abstract or pathological stuff, this definition of differentiability as well as the details of the chain rule recede back into the background, and the chain rule ends up, at least at first, being a very useful computational rule. Okay, so what else can we talk about? Oh yeah, let's go back to this one real quick. Basically, that means any theorem that we have derived, including this idea of directional derivative, can now be formulated just under the assumption that our function is differentiable, not necessarily differentiable or with continuous partials. Okay, so a graphical theorem that is pretty much unique to these presentations, that I derived to just explain to myself what multivariable differentiability means graphically, is that a multivariable function is differentiable at a point if and only if, for each parametric curve that goes through that point and which is differentiable at that point with non-zero derivative, the function f of c of t is differentiable at t equals 0, and the derivative of that function is what it should be, given by the chain rule, which is the gradient of f at that point times c prime of 0. And I think I should put c of 0 here. Let me fix that real quick. Okay, we're back. Thank you for your patience there. Here we take the gradient of f at c of 0 dot c prime of 0, and that basically, we're going to see that as we revisit our example, that can help explain things geometrically again a little bit more. The only other thing then is there is also a theorem that if a function has continuous first partial derivatives, and that is the most frequently used sufficient condition for differentiability. So if a function has continuous first partial derivatives at the point, then f is differentiable at that point. And this is basically the abstract justification for this thing that I've somewhat sloppily maybe mentioned every so often, which is that in applications, typically the hypotheses are satisfied. In a large number of beautiful and important applications, your functions will simply have continuous first partial derivatives, and that means all this stuff that we talk about here in terms of pathology and in terms of multivariable differentiability is moot, because continuous first partial derivatives give us that the function is differentiable. Now let's take a look at this geometrically one more time. And so revisit the example of this butterfly-shaped function. We want to show that this function is not differentiable at the origin. Well, here is the image one more time. And even though the composition with any differentiable non-stopping curve through the origin seems to be differentiable, and I've tried that out. I've laid all sorts of curves through the origin here, and I think they all actually are quite smooth, because the only way I could put a corner into the output would be if I put a corner into the input, and I can't do that if I go through the origin with non-zero velocity. So even though all of that seems to be differentiable, many of the derivatives simply have the wrong value, because the gradient of the function at the origin is 0, because we remember that the x derivative as well as the y derivative, the partials, are 0. And for example, the derivative of f of xx, which is if we're going in along the straight line y equals x, the derivative of f of xx, what would that be? That would be x cubed over x squared, which is x, and the derivative of x with respect to x, of course, is 1. So the derivative of that is 1, which is not equal to 0. So that's where this criterion that is pretty much idiosyncratic to me can also show you graphically how multivariable differentiability works, even in situation where the function is continuous and has partial derivatives, where it shows that, okay, the function still need not be differentiable in the multivariable sense. If you're interested in this, if you really like this stuff, that is certainly something where you want to take a class called Advanced Calculus or Introduction to Real Analysis, where mathematicians go through this with all the proofs that really then become very much required to appreciate all the details. We are going to, okay, that's gradient of f at 0, 0 in the direction of 1, 1, which is the direction in which we would take this derivative here. And we are going to finish with implicit differentiation. The implicit function theorem is another very deep theorem of mathematics that we're not going to prove, and what it says is that basically if we take a number k and we let f of x1 through xn minus 1 and xn, where we treat xn as a separate variable, as a different variable, we treat it differently from the other ones, let that be a function of n variables, so that all partial derivatives are continuous, and so that the derivative with respect to xn of f is not equal to 0. Then the function lowercase f that is implicitly defined as basically the level surface z equals, so that the function is constant on the level surface xn equals f of x1 through xn minus 1, so constant on the level hypersurface, if you will, xn being f of x1 through xn minus 1, that function is differentiable. And so that is the reason why anytime we obtained a function as a solution of a sufficiently nice equation, that function turned out to be differentiable. It turned out to be that way because the implicit function theorem guarantees it. The interesting thing is this implicit function theorem is actually quite sophisticated to prove, which is why we're not going to do that in an introductory calculus class, be it multivariable or not. And we're going to finish with a quick computational example. If I have a function z that is implicitly defined by x squared z plus y squared plus z cubed y squared equals 3, and I want to find the partial derivative of z with respect to x at the point 1, 0, 3, well, what do I do? Well, first of all, the point 1, 0, 3, 1 times 3 gives us 3, 0 squared is 0, and anything times 0 is 0 also, so that point is really on that implicitly defined function. Well, what do? We take our equation and we do the exact same process of implicit differentiation that we have done for single variable functions, except that this time y is a constant with respect to x is a constant with respect to y, and z depends on both x and y. The implicit function theorem just guarantees that this process will give us a valid result, but the process itself is straight computation. So what do? We take the partial derivative with respect to x on both sides. Partial derivative with respect to x of 3 is, of course, 0. On the left side, well, x squared z, that's a product, so we have to use the product rule. We take the derivative of the first, which is 2x times the second, which is z, plus the first times the derivative of the second, which is partial of z with respect to x. The derivative of y squared with respect to x is 0, so we get plus 0. And then we get a product, but the derivative, so y squared is a constant with respect to x, so this is really just a derivative of z cubed times y squared, and the derivative of z cubed has to be taken with a chain rule because z is a function of x and y, so in particular it has a partial derivative with respect to x, so the partial derivative is 3z squared, 3 times whatever is inside squared by chain rule, times the derivative of the inside, which is the partial of z with respect to x. Y squared acts as a constant, so it is just copied. We don't need a product rule here. And then we have equals 0 because the derivative of 3 with respect to x is 0. Of course, now we can factor out dz dx, and we can pull the 2xz to the right side. It doesn't want to pick it up. There we go. We can pull the 2xz to the right side. So we get right side being negative 2xz, and then we have dz dx as a common factor in all the other terms. So we factor that out, and we keep in the parentheses an x squared, which is here, and a plus 3z squared, which is here, times y squared, which we must not forget because it's part of that factor. If we then divide by this factor here, we really get an explicit expression for dz dx, which is negative 2xz over x squared plus 3z squared y squared. And if we want to find that partial derivative at the point x, y, z equals 1, 0, and 3, then even though the right-hand side depends on z, that is something that is not that much of a problem, because if the function is implicitly defined, we don't expect that we can solve for z, so we don't expect that we can get rid of this z in the partial derivative either. But that's not a problem, because at the point where we want to take the derivative, we also have a value for z, and so if we plug all that in, what do we have? Well, we keep the negative sign. This 2 is this 2. X is 1. Z is 3. X is 1. We keep the 3. Z is 3, which really doesn't matter that much for this term because y is 0. And we end up with a partial derivative of negative 6. And that finishes this example. And it also finishes this presentation. And it finishes this module in my presentations on partial derivatives. We are now going to focus more on what we're going to use partial derivatives for. We're going to talk about gradient fields, we're going to talk about optimization, and so on. Yeah, so if you look back at the topic of this presentation, then actually in terms of what I and your teacher can ask you to do, it shouldn't be that bad, because it's still back to taking partial derivatives and then using those partial derivatives in formulas for error estimates, for tangent planes for multivariable functions, and for tangent planes for parametric surfaces, as well as in implicit differentiations, which are all, even though the number of variables has increased and it's a bit more complicated, they are all computations that we need to be able to handle as we build up towards the meaning. There will, as we build up, well, we have built up towards and through the meaning, through multivariable differentiability then, but we're also then building up towards applications, of course. And so the multivariable differentiability part really is more background information. You want to know why people insist on various hypotheses, even if you won't work at that level of sophistication or pathology on a daily basis. With that, yep, you've got computations to do. You may have a couple of problems that are also looking a bit at the concepts, maybe a few things where you have to prove multivariable differentiability. Those will be the more subtle problems on the homework, I would venture, but either way, I feel pretty confident that you can knock most of this stuff out. I'll see you in the next presentation.